Okay, continuing on with our investigation of Einstein's insight into the fact that time is suspect. What we want to do next is look at an example called the light clock and see where that leads us in terms of what it tells us about how one person may observe time passing versus another person observing time passing. So here's the idea of a light clock. Let's look at, we've got two clocks here, Alice and Bob, both identical. Let's see what the idea here is of this light clock. So two mirrors set up, and we won't go into all the details of how we might actually implement this, but the basic idea is we have a light beam that travels up. We insert that. It hits the top mirror, travels back down again, and obviously then would keep bouncing back and forth between the various mirrors. And we'll say of this light clock, this apparatus, that one tick of the clock represents one round trip of the light beam. So it goes up, bounces off the upper mirror, comes back down, and when it hits the bottom mirror, we hear a tick. So it's just tick, tick, or tick-tock if you want to do the tick-tock noise there. So that's the idea of a light clock. Essentially just a light beam bouncing back and forth between two mirrors. It'll be traveling at speed c, of course. And if the mirrors are far apart, close together, it doesn't really matter. We just assume we have the necessary technology to actually record the ticks as the light beam bounces up and down. And Bob's clock, the same thing. So it has light beam going up, same light beam bounces back down, speed c. This distance between the mirrors is exactly the same. We know what that is in theory, or in terms of just the principle of the light clock. And therefore, we can find out more details about it as we go along here, as we shall see. So that's the basic idea of the light clock. Now what we want to do is set Alice's clock into motion. So we'll put it on her spaceship. She'll then be traveling with some velocity v. Bob will be observing in this case. And so this is our second situation here. Here's Bob's clock as Bob sees it. Again, no difference from over here. He's going to see the light travel up and down at speed c. So he's not seeing any difference. But now let's think about how Bob sees Alice's clock in motion. And a three-step process here. So say at time t equals 0, when the light beam is just leaving the bottom mirror of Alice versus a little bit later on, the top mirror is going to be over here. In other words, clearly the light clock is moving this way. As the light beam leaves here, this mirror is not going to be there anymore. It's actually going to travel over here and hit the mirror there, because that's where the position of the mirror at that point, as Bob is observing it. And then the bottom mirror will be here by the time it gets back down again. Long story short is the path of the light beam as Bob observes it. As we know it has to hit the top mirror, and it takes a while to get up there. If it missed the top mirror, then we'd have two different situations here, and something would be wrong. We'd have a contradiction involved. So we know it. Alice is observing her clock like this. As far as she's concerned, she's not in motion, so she just sees the light beam bouncing up and down like this. We know it hits the top mirror. Therefore, Bob also has to observe it hitting the top mirror. Otherwise, there'd be a contradiction. You can't have it hitting the top mirror for Alice and not hitting the top mirror for Bob. And so therefore, we know that since the top mirror is now over here, a certain time later, because Alice is moving with velocity v, that the light beam travels like that, hits the top mirror, and then to come back down to the bottom mirror, which has now moved to position 3, therefore, Bob will see it travel like that. So that's the path that Bob sees Alice's light beam travel inside her light clock. While his light clock is still bouncing back and forth very nicely like this, not going anyplace, just ticking away. So what can we immediately conclude qualitatively? We're going to look at this qualitatively, and then we're going to do a quantitative analysis of it and actually come up with an interesting result. So qualitatively, can you see what's going on here? We know that, and here's the key point, just like we saw when we were looking at the relativity of simultaneity and synchronized clocks, the key point was that the speed of light always travels at speed c. It doesn't have speed subtracted or added to it no matter what kind of motion is going on. So in this case, Bob sees the light beam. Alice's light beam travel diagonally up and then diagonally down, but he also sees it traveling at speed c. Light always travels at speed c for any observer, no matter what direction you're going. And therefore, just right off the bat, we can say that that's a longer path. For Alice's light beam to get from here up to there and down again, and then the tick occur, that's a longer path at the same speed as, compared to Bob's clock here, his light beam is just going up and down, up and down. Alice's takes longer to get there and longer to get back down again. What we're seeing here is that from Bob's perspective, Alice's clock is running more slowly than his clock. And yet the two clocks are identical when we have them side by side. They're just sitting there together, Alice and Bob, before Alice took off in her ship. They're working just fine, synchronized, keeping the same time. As soon as Alice goes in motion and then is passing by Bob at some velocity v, and Bob is observing her light clock, he sees her light travel a different path, a longer path to get from bottom to top and bottom again versus his light clock. So now that she's moving past him at velocity v, her light clock is ticking more slowly than his light clock. And this goes by a famous name. We're going to investigate this more, obviously, as I just mentioned, but just to give you the name of this effect that you may have heard about, time dilation. And another way to say this is moving clocks run slow compared to an identical clock that is not moving. So again, we have Bob's clock and Alice's clock, identical clocks. When they're at rest, they're synchronized, so they run just fine. Put Alice's clock in motion, though, and Bob's clock here ticks away nicely. Alice's clock, from Bob's perspective, is ticking more slowly than his now. Her moving clock runs slow compared to his clock. That's known as time dilation. Now, there's a flip side of it as well. You could say, well, but from Alice's perspective, Bob's clock is running slow, right? Because from Alice's perspective, she is stationary. It's Bob who's moving this way. And she could do this exact same analysis that we just did for her clock from Bob's perspective. She could do the same from her perspective on Bob's clock. And she would conclude that his clock runs slow. So this is one of the paradoxes. You say, well, wait a minute. How can they both conclude the same thing? There seemed to be a contradiction there. And yet, as we investigate this more, we have to hold that contradiction in tension, that seeming contradiction, because actually it really goes back to the whole idea of you can't define an absolute time. Simultaneity is relative. Clock synchronization is relative as well. To give you a very rough analogy, because to try to get our minds around this a little bit, think about everyday experience. If I see somebody far away, they look shorter than they actually are than if they're standing right next to me. If they're the same height as I am, they travel 100 meters away or something like that, they look short. Okay? You know, I could measure them with some perspective. They look about 6 inches high or something like that. And yet, they, observing me, my friend observing me, would see me as short. And you say, well, that's not a contradiction, of course. It's just how perspective works. And a little bit the same idea here. It's actually not a contradiction. It's just how the perspective works in terms of Alice observing a clock, Bob's clock, and Bob observing Alice's clock. So, again, not an exact analogy, but in common day, everyday life, our common sense perspectives, we understand the idea of perspective, something farther away is going to look shorter, because we're just used to it. We see it all the time. This we don't see in real life because we're usually not going that fast enough to see a difference between two clocks here, because in actual fact, this light beam going up and down, by the time we got to position 3, the light beam, in terms of getting up and down, it would not have moved very far. Just a tiny fraction of a meter, even a centimeter, a billionth of a meter is what would happen. By the way, something we'll probably mention later as well, speed of light. I may have already mentioned it, recall from last week about waves. But when we talk about the speed of light, easy way to remember, one easy way to remember it is it's about 1 foot per nanosecond. Okay, if you sort of a foot being 1/3 of a meter, roughly 1/3 of a meter, 1/3 of a yard. So 1 foot per nanosecond, 1 foot per billionth of a second. So if our mirrors here are 1 foot apart, it takes 1 billionth of a second to go up and 1 billionth of a second to go down, about 2 billionths of a second. And so Alice's clock, even if it was moving very fast from our perspective, maybe even supersonic speed, the time it took to take the light beam to go up and back down again, the mirror actually would have moved practically at all. It moved slightly, but not so much that we would really notice it. So that's why we don't notice these effects in our normal everyday experience. Okay, so that's introduction to the light clock and the idea. This is a qualitative analysis of it now. In our next video clip, we're going to do a quantitative analysis of it. But again, the idea is that two identical clocks, they both tick the same way, and you put one in motion, and Bob's observation of Alice's clock in this case, he's going to say, hey, Alice, your clock is running slow now. And she'd say the same thing about his clock as well. Now, I can guess some of you are probably thinking, well, this light clock thing and this idea of time dilation, this is a very special clock, right? Real clocks probably don't work that way. Well, later on, we'll have an argument showing that if a light clock works this way, then any clock has to work this way. Otherwise, we'll get a violation of the principle of relativity. So if the principle of relativity is true, we will see that given this behavior of this somewhat special light clock setup, then any clock, no matter whether it's a watch, a spring-driven watch, or something like that, any type of clock is going to, or pendulum clock, has to run the same way.